So next up, we have Professor Anna Slater from the University of Liverpool, who is a Royal Society University Research Fellow and Professor of Chemistry. And she's going to tell us a little bit more about her work in automation and flow. So I'll let you take it away, Emma.
Thank you very much, Becky. Hopefully you can see my screen. It's not showing the mighty. Excellent, perfect. All right, I'm really happy to be here. Thank you so much for the invitation. It's great to see some names I recognise, and I'm looking forward to meeting more of you as the AIchemy Hub progresses. As Becky says, my name is Anna. I'm based at the University of Liverpool, and I'm really interested in what automation and flow can offer, not just in terms of developing new techniques that we can use, but also how we can get those techniques used by chemists of all sorts of different disciplines, and how we can access those and really broaden the types of chemistry that benefit from these approaches. So I thought I'd start by showing you the wonderful people who've done all of the work that I'm going to talk about today. I'm really happy to talk about some of the work that we've been doing. So on the bottom here are our group at the moment, and at the top are some of our alumni who I'll be talking about today. I would say everybody in this photo pretty much uses flow in one way or another, and I've highlighted here some people who are what I would call our team automation. So we're developing our use of automation. So Firdaus, Harvey, Seda, Caitlin, Megan and George, and we'll be joined shortly by Jazz and Meg. So Jazz is part of an EPSLC project joint with Adam Clayton, Rich Bourne at Leeds and Alexei Lapkin at Cambridge, and it's great to see Adam in the audience, and Jazz I think as well, and Meg who's joining us as an RSC student, and I think I saw her in the audience as well, so we're really looking forward to welcoming you. I would say we're fairly late entrants to the world of automation and flow. I didn't do either as part of my PhD or my postdoctoral tenure, but I thought I would show you 4 case studies that we've sort of types of reactions that we've applied flow chemistry to get some benefit for each of these. So they're all loosely connected to supramolecular chemistry, macrocyclization, dynamic cage synthesis, like Annabelle's beautiful talk just now, crystallization, and a little bit of reversible coordination chemistry, just to demonstrate what we've been doing in this space. I thought I would start by talking about how I got into this. As I said, I haven't got any formal training in this area. I can pretty much pinpoint it exactly in terms of when I wanted to start using automation. And what really provoked it was this molecule here. So this is my nemesis. I was asked to synthesize this when I was a postdoc in my first year of a postdoc in Neil Champness's group at Nottingham. We were doing self-assembly on surfaces, and the idea was that we could make this porphyrin and we could do Ullmann type coupling with this reaction, this atom here, to form networks on top of a surface. And I've been doing lots of porphyrin synthesis. I did it for several years. So I thought, how hard can this be? Turns out pretty ridiculously hard. So, I mean, I started trying to make this molecule back in November 2010. And I started with a 10-gram formulation to make the aldehyde that I needed to make the porphyrin. I thought it was going to be fine. My yields were 0.03%, one of my first ones. And I spent the next 6 months trying everything to improve that yield to a happier place. I mean, porphyrin yields are notoriously low, but this was a particularly tricky one. And in the end, I brute forced it. I was like, right, I'm just going to make an absolute ton of this aldehyde again, and I'm going to do a massive 4-gram porphyrin synthesis reaction. And I can show you my lab book here. I'm not expecting you to read all of this, but I can show you. You can kind of guess my mental state from the state of this page. So you've got things like, oh, go on then. I clearly wasn't really keen to do this reaction, but mega dry chloroform, fresh from new dry slivs, very, very vigorous stirring, super dry DDQ. And if you can see all the way down here, I've written please 4 times. Please, 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 product. And enough, I did make it. In this case, I did make some of it. You can see at the bottom, Moldy says yes. But if I zoom this up here, Moldy, product present, but it fell out the bottom of the flask. And the swear word I picked there was not the swear word I said originally. So a couple of days had passed after I really got over this. I'd made a few milligrams of this molecule, and it just didn't work. And I remember thinking very clearly at the time, there's got to be a better way of getting this reaction to work, a better strategy of optimizing it, because all of my efforts, and I've done a lot of synthetic chemistry at that time, really wasn't working. And I thought, okay, maybe a new way of approaching chemistry might help us. So why is this reaction so difficult after all? Why, what are the problems here? And you may have done some porphyrin synthesis if you're in the audience. I just thought I'd go over a little bit of why, what is the challenge here? We start with pyrrole and an aldehyde, in my case, quite a sterically hindered aldehyde. And we do a condensation reaction, a reversible condensation reaction, not dissimilar to the imine chemistry in some ways of these two, with an acid catalyst. I was using boron trifluoride dietherate, but in this case you can use TFA to form this porphyrinogen, which you then oxidize. I was using a lot of DDQ, but you can use plechloranyl to this porphyrin species here. I think some of the double bonds have gone missing, but we make a porphyrin here. Now, if you have too much of your acid catalyst still lying around, you can get the protonated porphyrin, which is green, but if you don't, then you get this lovely stable porphyrin compound. You also have a side reaction here where your pyrrole can form polypyrrole. This is an irreversible side reaction, so once it's made polypyrrole, it's not going to go back. So this is a key sort of sink, if you like, for one of your precursors, and turns your reaction a horrible black goop. But that's not the full story either. So if you look at the seminal work of Jonathan Lindsay on porphyrin synthesis, you can see that not only do you get this porphyrinogen when you do this reversible condensation, but if you look at all of the other species that you get when you do this condensation and then oxidize, you form PAN, you form PANP. All these different products are all present in your solution. And if you look at the mass spectrum of a mixture, you can see the many different products that form here. So this is a porphyrin reaction where, with this concentration, with 10 millimolar of a catalyst, after 2 minutes, if you oxidize, you can see this is what forms your TPP, your porphyrin, tetraphenol porphyrin in this case. But you also have all these other products as well. It's just not, you end up with mixtures most of the time. So if you look at this over a time profile of when you choose to do that oxidation, you get to a maximum yield of your desired product, and then that drops off over time as either you lose some of your starting material to this pyrrole sink, or you just end up in other unobtainable things. So it's very important that if you want your maximum yield of your porphyrin, you want to do your oxidation in this region here, and not when you start to lose that yield. So let's have a look at mine in particular, my porphyrin chemistry. Again, so you do this reaction here to form your aldehyde, and then this is the transformation I was doing through a condensation and oxidation, and then quenching with triethylamine to get rid of that acid catalyst. And I found a paper at the time in 2007. They always say that an hour in the library can save you 6 months in the lab. I did find this quite early on in my 6 months, I will say, of trying to make this molecule, where they were trying to make mesotetraanthral porphyrin, which is just the same without the bromines, right? And this was successfully synthesized in the dizzying heights of a 3% yield by using this kinetically controlled Lindsay method, where they did their oxidation only 1 minute after the condensation of the pyrrole and the aldehyde had been initiated by addition of the acid catalyst. And if they left this any longer, the yield of the mesoporphyrin went down and made separation and purification more difficult. If you've done any porphyrin separation, it's already quite difficult. So if you're making it more difficult, you're not in a happy place. So essentially, if you look at the graph I showed of the porphyrin reaction over time, the maximum you're aiming for here is a minute or two after you've mixed those two components. So very, very challenging, particularly to do at scale. So my 4 gram reaction, it's going to be very, very difficult to really control that process. But there are other options, and as Annabelle very articulately pointed out, high throughput screening can really give you a lot of information here. So I thought I would show you Jonathan Lindsay, again, a paper in 1999 where they did exactly this. They did a high throughput screen for this porphyrin here, which is similarly awkward to make than the one I was looking at, where they've done this scientist in the loop optimization, where you've got your workstation, you get all your data, you do some closed loop evaluation, and you use a resource manager and a scheduler. So back in 99, to look at exactly this reaction. So they looked at very similar things. They porphyrin yield over time. They plotted things like using different solvents, different quantities of your acid catalyst. And they used this. They did a really comprehensive study of these conditions to forming this trimesotyl porphyrin. They did 11 experimental grids, 284 reactions over a 10-week period, 1,704 data points, and they did not increase the yield of the porphyrin. And I say that not because this is a bad experiment. It's not. It's an excellent experiment. It really does show you that you can change a lot of different conditions. You can influence the outcome of this reaction, but maybe you've just reached the maximum, you might think. But I think this comes back to Annabelle's point as well. You might just not be looking in the right part of chemical space. And I think that's where flow chemistry for me has really helped in this situation. Because there's only so much you can do on this platform in terms of this chemistry. What you might need is a completely different approach. So if a reaction works in batch, you should do it in batch. I would be the first to say that. What you want to do, if you want to control your relative concentrations or your mixing, or you might want to go to high dilution, a sort of very typical supramolecular chemistry type technique is to use slow addition or high dilution, where you're essentially controlling the addition of one of your components to the other in this case. And really all I'm saying is perhaps you might get even better control if you move to a fully continuous process where you're adding your two reagents, mixing them at a controlled point, letting them pass through a heated reactive zone and collecting at the end. That might give you even better control over your process. So I'm not going to do a deep dive into the background of flow. I will point you to this very helpful review by Peter Seeberger's group, The Hitchhiker's Guide to Flow Chemistry. It's something that our group always get given when they start. It's an excellent review covering lots of the theoretical background and also how flow has been applied in different places. But I also want to just note, if you are thinking of getting into flow and you're doing one of those fields of chemistry that aren't immediately suitable, such as materials chemistry, crystallization, supramolecular chemistry. I wrote this review with Andrea Leybourne and Karen Robertson, both at Nottingham, which I mainly point out because I love Andrea's title, Quid Pro Flow. I thought as soon as she said it, I thought that has to be the title. It's amazing. So this is a sort of guide to how you might get into flow if you're not doing organic synthesis, where it's quite well established. And I do want to just point out some advantages of flow that might help us here. So you can access wider process windows in flow. We are under pressure. We use back pressure regulator, so you can heat solvents much hotter than you might be otherwise able to. We routinely use DCM at 100 degrees, no problem. So that means you can access those areas of chemical space that aren't so accessible otherwise. That temperature can be very well managed. You're using a narrow pipe. Heat is dissipated easily, and you can actually heat very quickly. So you get excellent temperature management, which might matter for your selectivity. You can telescope reaction steps because flow is time resolved, essentially. So you can really precisely time when you mix something, and then you can mix something again later down the line. And you can generally control whether that mixing is very efficient or is controlled only by diffusion. And I'll show you a bit about that later. You can also use inline analysis and automation because you can measure a point in your pipe 1,000 times in a run, and in theory you'll be measuring the same time point in your reaction every time, which can really help get that information out about your process. And in theory, if all of your pumps are calibrated and you're doing the same thing every time, the reproducibility should be very good. And ideally, your process should be scalable, because if you want to collect more of your compound, you run your process for longer and it will be collected at the end. There's a lot of method development between the idea and getting all of these advantages, but these are some of the things that you can get out of transferring a process to flow. So when I was a postdoc trying to make this awkward molecule, I saw a talk by this guy. This is Professor Harris Makatsaris, who was at Brunel at the time, now at KCL, I think. And he gave a talk about how they use flow chemistry for some of the chemistry that they were doing. And I contacted Harris and said, I'd really like to try flow chemistry for porphyrins. I think it might work. And we had a little go. So this is some work with Leonid Paramanov, who's a postdoc in Harris's group, which we did in 2012, where we were making tetraphenol porphyrin using syringe pumps in this case, and their oscillatory baffled flow reactor, where you can it has a pathway through the middle of this unit here. So that worked pretty well. We were using inline UV detection to find our porphyrin, but as fixed-term contracts do, my fixed-term contract ended where I was at the University of Nottingham, and I moved to the University of Liverpool without really finishing up that part of the work. So it was a promising proof of concept result, but it didn't do what we needed in the end. So in between leaving Nottingham, this lovely paper came out of Momo's group, the De Oliveira, in 2015, where what they'd done was make TPP in flow from pyrrole and aldehyde again, using what's called the Gonsalves method. So this is where we use nitrobenzene and propionic acid, which acts both as an acid catalyst and also the oxidant. So essentially you are doing your condensation and your oxidation pretty much simultaneously. So a common TPP yield, no matter how you make it, is about 40%. This Gonsalves method normally gives about a 20% yield, but has the advantage of scalability. And in flow, they actually managed to improve that yield all the way up to 31%. But this is the bit that really pricks up my ears, is by optimizing flow rate, temperature, and residence time, they managed to get a space-time yield of 8.2 grams of porphyrin a day. So even if your yield is poor, you can get enough of it by running your process for longer. But what I wanted to do, and this is what Henry, our first PhD student in the group, who does smile, I promise, was to separate out those two stages, the condensation and the oxidation, so that we could get that precise timing of when to stop that reaction and get the maximum yield of the porphyrin. So I asked Henry to transfer the method of making TPP into flow. And this is what we've got here. So your pyrroles here, your aldehydes here with your TFA catalyst. You pass it through these two pumps, mix it a T-piece. You have this first reactor, which you can heat to do the condensation. And then you have your oxidant coming in for the second stage here, where you've got your oxidation happening in your second coil. It goes through your BPR, so we can heat our DCM to as hot, well, reasonably hot. And then we're quenching at the end in triethylamine. So Henry did some work to look at the impact of concentration, residence time in the first reactor, temperature, and equivalence of TFA, and he got the yield of the porphyrin up to about 42% in this case. But we can already see that there's a problem with this method. We're getting green on our column where we're purifying offline. And that means we've got some of that protonated porphyrin that I said was possible if you've got a little bit too much TFA going around. There's an issue with our quench. And we can also see that we're losing some of our porphyrin in the workup. So our yields, although they look pretty good, they may not tell the whole story. So some work there, so Ross and Harvey did, was to iterate on this process. So now we've got our condensation, our oxidation, and now a quench in line in our third reactor. And we have our inline UV vis analysis that can tell us, do we have any of this green porphyrin by its shift in the UV to a different lambda max, and then sort of compensate for that on the fly. So this is what it looks like in practice with our 4 pumps and our 3 reactors, our UV spectrophotometer and our UV cell here, monitored on the software on the Vaportech instrument. And now you can see, if you look at the comparison between the flow pathway I showed you on the previous slide and this one, for TPP, we're getting pretty much the same answers. But we can now see if we get something like this off the UV, we know we've got protonated porphyrin and we need to tweak that triethylamine flow rate to make sure that we're doing our quench properly. And you can also see that for a substrate that might be very sensitive to having acid hanging around, our previous process, we actually saw a decrease in yield when we increased our equivalent of TFA, whereas by our analytical yield on our fully continuous process, we actually managed to get this up to 45%. So now we have a platform where we can reproducibly make and thoroughly understand and analyze the output of these porphyrins. What Harvey's doing now, alongside Prof and others in the group, is equipping this with an automated optimization algorithm to close the loop and do autonomous optimization of porphyrin synthesis, which we're very excited about. We may not go back to my nemesis, but we might. So if we can do this for this type of reversible reaction, maybe we can do this for other types of reversible reaction, like the one we saw, the ones we saw Annabelle talk about. And I'm going to mention this cage, which was made by the Cooper Group back in 2009, I think, called Cage 1, the first one. And this is a mixture of triformylbenzene and ethylene diamine in this case. Now, if you did this on Annabelle's rig, you would definitely see a whole lot of polymer if you did it at a higher dilution. So I'm definitely going to get one of these vision robots. This sounds awesome. So this can make a nice cage, as you see the crystal structure down here. But if you don't do it at high dilution, at cold temperature, and over a long period of time, you make a lot of polymer. I mean, if you think about it, this is a flexible diamine. There's no reason really, other than thermodynamic stability of this product, that you would ever form anything discrete. It's very possible that you'll form polymer. So can flow help? Can flow help us avoid those high dilution conditions? So this is some work that I did some time ago in collaboration with Steve Lay's group when I was still a postdoc in Andy Cooper's group. Just looked at, if you transfer this to flow, can you maybe up those concentrations a little bit and still get the cage out, or will you make a lot of polymer and block up your flow reactor? So what we've got here It's ethylene diamine in the solution of methanol and DCM, and triformylbenzene, again in DCM, mixed at a T-piece, heated in a coil at 100 degrees for 10 minutes residence time, and collected at the end here. And very happily, we formed this in 93% yield. That's not to say that you can't make polymer in the flow reactor. I found that if you replace this mixing piece with a serpentine structure, you can fill that with insoluble polymer very quickly. But it seems like you're getting some advantage by moving to flow. So if you look at the comparison between batch and flow for this reaction, in batch you use more solvent and a lot more time, but in flow that is vastly reduced and you get the same purity and yield. And I think what's going on here is actually the mixing in this T-piece is really poor. So you can see here from this paper that I found that has this nice figure. This is what happens when you mix two solutions at these types of flow rates in a pipe of this sort of diameter. You can see that the mixing is really only at the interface of those two if you're under laminar flow conditions. So actually in this case, because mixing and concentration gradients are important, we think the reaction is diffusion limited because it is so rapid once that amine and that aldehyde meet each other. We can use flow to slow down that mixing and gain control without going to very high dilution. So that brings me on to my third case study, which is if we can control mixing, and that helps us for these types of cage reactions, what else can we control? And maybe what we might like to control is the crystallization of these cages. So something that you may know already is that if you form, it's like Annabelle was saying with cyclohexyldiamine and triformylbenzene, if you choose the RR enantiomer of your cyclohexyldiamine, you form the R enantiomer of cage 3 in this case. If you choose the SS, you form the opposite enantiomer, cage 3S. But if you mix these two, they immediately precipitate to form a racemic structure, a porous structure, which has this yellow pore topology going through the center. So this is a video taken by my colleague Tom Hasel when he was a postdoc in Andy's group of just how quickly that happens. So if you take a solution of both of these cages and you mix them together, you will see you immediately form a solid, which is great if you're impatient, but it's not so great if you want to control that process in any way. A rapid crystallization is not generally a well-controlled crystallization. So what can we do about that? Well, Tom in this paper back in 2012 had a look at the impact of changing the conditions on that crystallization process. So if you warm it up or you cool it down, you can change the average particle size. This is measured by DLS. And you can see the impact of that on the SEM as well. So at 30 degrees, you get these larger crystals, and back down at -80, you get very, very small particles here. He also looked at the rate of mixing, of adding one cage solution to the other. And the faster you go, the more you get these spherical particles, whereas if you do it slow, 0.25 mils per minute was pretty much the slowest that he could do on this, again, a high throughput screen. You get these much more diamondoid morphologies. And you can equate the morphology of this as how these cages pack together. If you have a spherical particle, you have a crystal that's got lots of defects. You may have missing cages. Your porosity actually goes up in this case. If you have nice diamondoid shaped particles, these sort of tetragonal type things, then you have a much more crystalline material, which might be better for separation, for example. So you have that pore going very nicely through. So Tom drew this graphic where if you go for cold and fast, then you get small spherical particles, whereas if you go for hot and slow recrystallization, you might get these much nicer sort of diamond shape, and it depends on what you want, where you might want to be. But you'll notice he never really got to this shape. I think the best you can manage with the setup is around here, where you have these sort of rounded edges, which might not be good enough for certain separations. So we were interested, and this is some work that Becky did as well. Becky started when we were both in the group. And this is something that we wanted to take on further. This is Nick, who also smiles, I promise, who was looking at whether this could be controlled better in flow. So he built this very simple flow reactor where you have the cages in solution pumped together. You can heat not just after the mixing piece, but also before the mixing piece to make sure that those two streams are already at temperature when they meet, which is important. And then you can collect this via inline vacuum filtration to get your cage solid at the end. We can go to higher temperatures and lower temperatures, so minus 60 to 150 degrees is no problem in this setup. Our reproducibility should be improved and our mixing should be quote unquote worse. We can look at residence time and temperature, and we can also look at whether we preheat or not. And I'm just going to show you some of our results here, which looks at different residence times and temperatures. So along the bottom here, we have a residence time of 1 minute, 2.5, and 5. And you can see that when we do that at very cold temperatures, then there's very little impact on the particle size, no matter what the residence time is. But when you do this at 100 degrees, you can start to see differences in particle size, which is small to large along this side, when you change that residence time as well. So if I then plot one of these runs, I think it's the 5-minute run on just a XY plot, you can see that these are the batch conditions that Tom explored, and these are the flow conditions where we get a more gradual change, which is more controlled, and we can access different parts of the size. We can do this with a little bit more detail if you like. You've got more control over the dial. And actually, if you look at 100 degrees at 5 minutes, now we are starting to get those very nice crystalline particles, which indicate that we're getting more control over that crystallization process. So we can scale this up, and you do see a change in the gas sorption properties. And what else we can do is we can take all of our data from all of the different runs that he's done, and we can throw this into JMP, so Design of Experiments software, and we can get it to predict, okay, if you want a particle size of, I don't know, 325 nanometers, then what conditions should we use? Now, we could have done that the other way around. We could have done DOE to tell us which conditions to look at, but we wanted to establish first that this method was reproducible and understand, was it even possible to get into flow without taking the blockages? So we've done it without getting blockages. So we've done it kind of the other way around now, but you could equally do it, with Design of Experiments first, which would incorporate a measure of reproducibility as well. Anyway, so we did this and we run the experiment, and then our DLS tells us we had particles of about 300 nanometers and our SEM says 387. So given that DLS we find tends to underestimate and SEM tends to overestimate, we believe we're in the right ballpark. And you could start to say, all right, well, now I want this particle size with this morphology, and you can start to interrogate that data and scale up the ones that you want. So I want to finish with this last example. So we've done crystallization, we've done macrocycles, cages, and crystallization. I'd just like to finish on this last example, which is about what about other reversal processes? And Annabelle also mentioned this with metal ligand cages. And this is a collaboration with Professor Liang Chong at East China Normal University, where we wanted to see whether we could use flow to gain some control over the formation of these metal helicate species. So the pentamer shown on the right here, and a hexamer shown on the left. These can then be subsequently subjected to ring closing metathesis to form these molecular knots, which are shown in cartoon form here. So this is work established by the Lee group and Jean-Marie Lane and many others in this area. So what's the problem with these reactions at the moment? Why would you want to transfer them to flow at all? So here's my cartoon of the ligand that Liang's group made, and Chen Du was the lead on making this ligand. You can, if you use one iron salt, iron chloride, form this pentamer. You can do that in a 71% yield. Typically, though, it's done on a very, very small scale. And if you try and scale up these reactions, you find that you don't get the same results. Your selectivity or your yield suffers. So the chloride here, it helps to template the formation of the pentamer. If you use iron sulfate in a much higher temperature, you can form this hexamer species. However, if your iron equivalent's not quite right, so if you've got more than 1.1 of iron salt, or your conditions aren't quite right, you form this trimer as an undesired side product. And we find that if you don't, in many of the conditions that are tried in batch to increase the yield, you end up not just getting pentamer, but also trimer, and they're quite difficult to separate. So we want to do two things. We want to improve the selectivity, and we want to achieve a higher throughput of these species. Because if you can't make multiple grams or multiple 100 milligrams, then it's very difficult to test their properties for some of the applications that they might be really exciting for. So me and Liang met at a mask meeting and discussed trying this in flow. So Alex Pajim led on this in our group, and this is the flow reactor that he ended up with. So here we've got a ligand here and our iron here, and this was accepted. It was published in Chem on Monday. So just out. And what we have here is a very similar thing where we're preheating those two streams and we're mixing, going through this heated coil here. At this point, we have a quench, this potassium phosphate, potassium PR6 solution, which quenches at the end. And then here we can form this hexamer species from these optimized conditions in a 47% yield, which is lower than you might expect, but in 162 milligrams per hour, so much higher throughput. And in this case, the only other species that is produced is the starting material. So if you have starting material and hexamer, then you can send that starting material back through. So 99% selectivity, 162 milligrams per hour. You can also do the ring closing metathesis in flow. So these are not optimized conditions, but you can get this up to 85% at the moment, which gives you 345 milligrams per hour rather than tens of milligrams in 24 hours. We change the conditions. So here we're just changing the temperature and the salt, and you can form the pentamer in 282 milligrams per hour. It's a residence time of only 16.7 minutes. So again, this is, we think, a much more tractable way of making it than the batch setup. And again, you can go through and do the ring closing metathesis. I'm really excited about the opportunities to optimize other species here rather than these known ones. And one of the first things we've tried, so these are the two ones I've just shown you. One of the first things that we've tried is making the zinc variants. So the zinc pyridyl interaction is much more labile, more reversible, and it's much harder to make that a selective reaction. So the normal way of making these types of knots with zinc and not iron is that people have made this, replaced the metal, also taken the iron out, put the zinc back in, which is obviously many steps and not a very straightforward way of doing that. So we thought we'd see, can we use our flow conditions to go straight to the zinc? And unfortunately, the best selectivity that we got here still had 30% of this undesired trimer species. It's better than you can get in batch, but it's still there. But just by chance, Alex tried sonicating it, and turns out that when you have a mixture of all of these three, if you sonicate it, then this crashes out on its own. So it's a different route to this without having to go via this extended method. So this is a precursor for this zinc, not by ring closing metathesis, but you can also do transmetallation to get some other more exotic things. So we're very excited about this. So I've shown you these four kind of case studies on how to get a method into flow. But there are plenty of other processes to try. I think we are interested in reversible covalent chemistry, macrocyclization, cage formation, and other non-covalent processes. But I think what all of these things have in common, and a lot of supramolecular processes, is that when you're exploiting these weak and reversible interactions, that you might even be doing classic host-guest chemistry, you might be doing self-assembly on surfaces like my PhD, and you might be crystallizing an organic material. Their formation is really strongly influenced by their environment. So you just may not get what you need from a round bottom flask. It makes them hard to make, particularly at scale, but it also makes them ideally placed to benefit from flow techniques and automation. And I would say I haven't really spoken about our work on automation here, but you can imagine that once we have a method, the power of inline analysis and optimization. So you start with method development, benchmarking, and inline analysis. And then, of course, once you have that, we can start doing kinetic studies, screening, and even autonomous optimization. So nice to share an example from Leeds and see Adam here, where you can do optimization, for example, catalysis, nanoparticle production. Ultimately, all with a view of getting enough of these materials, these exciting and interesting materials, to test, to scale up, and to actually fulfill their potential as functional materials. And that's really, so the studies I've shown you are all here, but these are the things that we're doing now to try and make enough of them to really show what supramolecular materials can do. So if you're interested in trying flow, we would welcome, and if you don't have access to it already, we've got a flow centre here at the University of Liverpool, which is available for collaboration, including several flow reactors with different capabilities and different methods of inline analysis. So please do get in touch if you're interested. And it just remains for me to thank the very many people who have done this work and contributed to this work. And thank you very much for listening to me go on about it.